one โอเคไปแล้วครับ Okay yes the chapter 6 talks about nuclear physics and particle physics as the name suggested here. Okay, two main topics, but both topics are quite close to each other. Yes, and we will talk first about the nuclear physics. Okay, in the nuclear physics, there are so many topics we will see. The first one is the nuclear size, which is the, okay, before we have considered the atom, right? It's the, we have seen the atom size, which is on the order of angstrom, right? It's 10 raised to negative 2. So in this chapter, we won't talk about the electron orbit anymore. We will see something at the heart of the atom, which is the nucleus. And I'll zoom to YouTube. And then the nuclear size will be much smaller than the atomic size, because the atomic size includes the electron orbit, right? And that causes the atom bigger. So it's not the case right here. We will see something at the heart of the atom, so it's going to be smaller. All right. Yes. ที่ channel Zoom to YouTube นะครับประภาวิทย์น่าจะเป็นคนแรกนะผมเข้ามาช้าไม่รู้ว่ามีใครพิมพ์ก่อนหน้านั้นหรือไม่นะครับถ้าใครมีพิมพ์มาก่อนหน้านั้นก็โปรดแคปเจอร์หน้าจอไว้นะครับที่ Zoom to YouTube นะครับ Okay. Yes, the nuclear size is much smaller than the atomic size, and we will talk about some mechanism that happens in the nucleus of the atom, which is nuclear force, and something which is not far from the nuclear force is the nuclear mass. Okay, nucleus mass. We'll talk about the mass of main subatomic particles inside the nucleus, which are neutron and proton, right? Everybody know that in most or in every atom we have proton and neutron, except for the basic hydrogen, okay, that has only proton. Apart from that, from deuterium, which is which is a bigger isotope for hydrogen that has also neutron, is the first atom that has neutron. Okay, and it includes neutron. Okay, except for the hydrogen. Okay, and nuclear mass is something about the mass of proton and neutron, and after that, in order to form the nucleus of the atom, we will have something which is called binding energy, and binding energy is related to the mass that is lost. Okay, that is the atom has consumed. Okay, reduce its mass, so that the reduced mass is transformed into the binding energy. And what is the binding energy? Binding energy is the energy that is used to attract several particles like neutrons and protons together to form up the nucleus of several atoms. Okay, and this is the mechanism that the nature has created nucleus of the atom. Okay, after that, as you know, once you have bigger and bigger atom, the nucleus size is big. The nucleus is big because it contains a lot of neutrons and protons, but sometimes the atom, the nucleus is not stable because the nucleus is too big. Okay, and the nature tries to reduce the nucleus by to reduce the nucleus by releasing the energy, and the releasing the energy is in terms of several particles like alpha particle, beta particle, and gamma ray. Okay, and yeah, the big nucleus try to separate itself to be a smaller nucleus, to not us, to fill smaller nucleus and nuclei, sorry, and yeah, they will release some particles, not some, three main particles. The first one is alpha particle, the second one is beta particle, and the third one is the gamma, which is not actually the particle. Gamma is in the same class as the photon. Okay, it has no mass, but it gamma is included as one of the emitting particles from the radioactivity, and that's the activity of the big nucleus that try to be separated into smaller one. Okay, let's go to the idea of radioactivity. We have to consider the decay rate, which is the rate that's the amount of emitting particles is reduced. Okay, and we would have some how the word half-life, okay, which means the time that the amount of emitting particles reduced to half the original amount. Okay, and once we study so many things about radioactivity, one of the prominent application, one of the obvious application is the carbon dating. Well, what is that? Human tries to use the ratio or the portion of carbon. You know that carbon has several isotopes, right? The basic one is carbon 12, and we have also carbon 11, carbon 13, carbon 14. And the scientist uses the mixture between carbon 12 and carbon 14 mainly, okay? Mainly two isotopes of carbon. And if we consider the portion of this mixture, we could estimate or calculate the time that object lasts, okay, from the past. Okay, and that's called carbon dating. Okay, we use carbon isotope to measure how long an ancient object has been created in the past. Okay, and that's the whole thing about nuclear physics, the first section of this chapter. And the second one is particle physics. Okay, I would say honestly that this is not finished yet, because last year your elder colleagues, your elder schoolmate didn't have so much time, so this section has not completely been prepared. Okay, was not completely prepared. Okay, what is the meaning of nucleus? Well, what is the meaning of nucleus? If you go to the dictionary or you look at the encyclopedia or something like that, it means that the core or the central part and of something, okay, or round, okay, and which others are assembled. Okay, it has a round shape. It is in the central part. It is the main stuff of anything. And yeah, several things are assembled to the nucleus. Okay, and that's the meaning of nucleus. What is the difference between nucleus and nuclei? Well, it's, you know, nucleus is the ancient word. It's derived from the Latin word. Okay, so yeah, yes, it derives from the Latin word, and one of the rules in the Latin is that when you end up the word with us, if you want to make this singular noun to be plural noun, you have to replace us by the letter I. So it's going to be called nuclei. Okay, the singular form of nucleus is nucleus. The plural form of nucleus is nuclei. Okay, it's like you have mango and mangoes with the ending of es or something like that. Okay, nucleus is just the singular form, while the nuclei is the plural form. Nucleus is a collection of particles called protons, okay, and neutrons, right? The difference between protons and neutrons is that the main major difference is that proton is positively charged. Okay, proton has a positive charge. Neutron has no charge at all. And one minor difference is that neutron is a little bit heavier. Neutron has a little bit more mass than protons. Okay, and once the both stay together inside the nucleus, okay, and when the number of proton is greater than 1, is from 2, 3, 4, right? And the neutron is, then the number of neutron is also greater than 1. The difference is that proton will have the repulsive, okay, the pushing force to each other, okay, and yes, because they have the same charge, right? The protons have the same charge, and any charge that has the same polarity is going to be, it's going to try to put each other, okay, to separate them from each other, but they cannot. Okay, neutron has no pushing force at all, no repulsive force at all. The amount of pushing force, not in the opposite way to the attractive force, is given by the Coulomb force. Okay, you could derive the Coulomb force. Okay, that's the main thing about two subatomic particles, protons and neutrons, that form up the nucleus. Okay, we will talk about something that is related to nucleus. The next word you may have seen if you read so many books is that the nucleon. Okay, nucleon is the general word you may have ever heard. Nucleon is the word that could be either proton, that could be referred to either proton or neutron. Okay, it is up to you, and it depends on the context around these word. Okay, whether it means proton or neutron, but both of these form up the nucleus. So to refer to the particle, the physicist would refer to the ending word as on. Okay, on. Okay, and that's why we have nucleon. Okay, in the nucleus, A, Z, xn. This is the standard representation of the elements, okay, on the from the periodic table, you know, periodic table, right? From the chemistry. Let me see anything that may happen in line. Okay. Yes. Because we have so many เราอาจารย์เข้าซูมอยู่ครับโอ้ขออภัยครับ sorry for that เฮ้ยพีระดลคือใครครับฮัลโหลครับพีระดลเดี๋ยวพีระดลคืออัครวัตรเหรอเดี๋ยวนะครับพีระดลเดี๋ยวแป๊บนึงพีระดลแสงคุณนี่คือใครอ่ะพีระดลLet me check the surname. Maybe it is one of your parents, or I'm not sure. Class attendance 2012 เป็นซูมของคุณพ่อผมครับโอเคคุณจะเข้าเองหรือคุณพ่อจะเข้าใช่หรือไม่ครับโอเคโอเค it's no problem let me remove okay okay yes, let's continue our story. Okay, the base, the standard symbol or the standard representation of the nucleus of the atom in chemistry. Okay, both physics and chemistry use the same notation, oblique cross notation. Even in chemistry, the chemist would often neglect the information of Z because Z is well known for them. Okay, once we say we write down here the letter for X at the X location, they would be able to remember the number of protons here automatically. So it's sometimes the information of Z here is neglected in chemistry, but for us in physics, we are gonna assume that we are not familiar with the atom symbol, so we would somehow always leave the information of the number Z here. Okay, so what is AZN? A is the mass number, okay, and it is equal to the number of nucleons. Okay, you know nucleons. Nucleon can be either proton or neutron. So it could be neutron or proton. Okay, it depends on the context, but it's the atomic particle in the nucleus okay, and that's the meaning of nucleon. So the number of neutrons plus the number of proton is known as the mass number A, which represent on the left hand side. It is the left superscript, okay, and Z is well known, right? It's the atomic number, which is the identity of that element, okay. Each element had its own number Z, the atomic number, and simply speaking, you have Z. The number Z is equal to the number of protons. For example, if you have hydrogen, you have only a single proton, right, and one electron moving around, and that's hydrogen, okay. But if you have two proton and you have two electron moving around the nucleus too, okay, this element is no longer hydrogen, it is called helium, okay, and so on, lithium, blah blah blah, okay. Yes, the atomic number that is equal to the number of protons, okay. If you go to the periodic table, yes, the main table for the chemist, okay, the main table in chemistry, okay, all right, yeah. Oh no, it's written in German. Oh my God. Periodic table. Yeah. Okay. If you have a single electron, single proton, it's going to be called hydrogen. Okay. And the next one, if you have two electron, is going to be called helium. It's noble gas. The atomic number is the number of proton in the nucleus. Okay. Only neutron. Oh, sorry. Only proton. Okay. Only the number of only proton at the heart of the nucleus, at the heart of the atom, okay, heart, in the nucleus. Lithium is the next one that has the 3 protons, okay, 3 protons, and beryllium is the next one that has 4 protons, and blah blah blah. Once the number of protons changes, the symbol of that element is also changing. You could see here He helium, Li lithium, Be beryllium, and then boron, carbon, 5, 6, 7, the number of protons, nitrogen, oxygen, fluoride, and neon, right? When the number of proton is 10. You go further and further until you get a big element like this one, I don't know, flerovium. Space is a strange element, okay, but due to for us in our chapter, we would arrive somehow at deuterium, rhodium, palladium, and silver cadmium. This is the big metal, right? Mercurium is what we have already considered it before. Platinum, gold, and so on, right? Radon is over here, and what else? Why? What happened? Who is that? Oh my God. Yes. Yeah. I need to get back to monitor sharing rate and get back to this one. Okay. Oh, moment. This one here. Okay, right. Yes. In this chapter, we may consider the spatial elements like uranium. Yeah. Okay. Uranium, thorium, which is the source of radioactivity. We are going to see. Okay. Uranium, thorium, and anything else. Nothing more, right? Only this one. Okay. Please remember thorium and uranium. The atomic mass, atomic number as atomic numbers as 90 and 92. Okay. The next one we will go to this, right? The atomic numbers that is equal to the number of protons. Again, that's what you have seen when the number of protons changes. We change the symbol of that element right here. Okay, the neutron number in. Let me check whether the sound works well or not. Test 1, 2, 3. Test 1, 2, 3. Okay, เสียงไปนะครับ โอเคมีคนพิมพ์มาที่ซูมนะครับก็น่าจะเป็นอัครวัตรนะโอเคyes ชัยสิทธิ์อัครวัตรนะครับ and let me send you, otherwise I'm gonna forget. Okay, this one here. Oh, yes, 908. Okay, yes, yeah, the next quantity is okay. This location is called left subscript, right? This is right subscript, left subscript, and let's move to the right side. It's called right subscript, and simply speaking, subscript. Okay, subscript notation. Okay, at this location we have the number n, right? The capital N, and of course, the reason why we use the capital N is that มีใครจะเข้ามาที่ซูมอีกไหมครับเดี๋ยวผมเข้าไปเช็คดูนะครับไม่มีนะปกติจะมีคนที่ชอบเข้าซูมอะไรอย่างเงี้ยนะครับก็ไม่มีนะโอเคokay, all right. Where is that? This one, right? Okay, the next one is the letter N, right? The reason why we use letter N is that it represents the number of it simply represents the number of neutron. Okay, and I don't understand why. Oh. Okay. Yes, because we refer to the number of neutrons, and that's why we use the what happened? That's why we use the letter N. Okay, the capital N, because it means the number of neutron. Okay. Yeah. if you get confused, okay, that representมีใครพิมพ์มาที่ channel นี้ด้วยthat represent the atomic number, which is the most important one. It's the heart of this notation, because it's equal to the number of protons. And next one is the result from both numbers. Okay, if they don't write the number in, you can still understand these elements. Okay, you can just make the subtraction between A and Z, and you're gonna get the information in easily. Just compute A minus Z, and you get capital N. All right. Let's say, for example, N is the number of neutrons, right? Let's say, for example, we have 27, 13 aluminum. Okay, you could see here that they don't even write down the number of neutron at all, right? They don't write down the number of neutrons at the right subscript, but you can infer, you can get the number of neutron by yourself, okay, easily by using the subtraction between A and Z, right? From this notation, from this relation. 27 minus 13, right? It's going to be 14, and that's the number of neutrons staying at the nucleus of aluminum. All right, where is aluminum? Aluminum is, oh, what happened? 23, right? Oh, 23 and 27 aluminum is 13 here. Okay, 13 right here. And yes, there's nothing more. Yes, 13 aluminum, right? They don't write down the atomic mass because it depends on the isotope. That's for chemistry. For us in for us in physics, we write down everything, right? The full information, because we pay attention to the nucleus. Okay, to the nucleus. That's why we consider everything. The mass number, which is the number of nucleons at the heart of the atom, or at the in the nucleus, right? 14 is the number of neutrons after the subtraction, and the number of protons are at the nucleus. Okay, in the nucleus is 13. Okay, and if this number changes, we wouldn't say that element is aluminum anymore. Okay, it's going to be different element. And in chemistry, they often omit the subscript Z. Okay, and it's sufficient if you just write down aluminum. What happened? Who else? Huh? แล้วก็โทรไปนะครับแล้วก็pressure start โอเคก็ขอแจ้งเหตุขัดข้องนะครับเขาก็พยายามโทรมาติดตามผมนะว่ามันใช้ได้หรือยังคือมันใช้ได้แล้วนะครับตั้งแต่เมื่อคืนนะครับก็ขออภัยด้วยนะมันรบกวนชั่วโมงการเรียนของเรานะครับ Okay, yes, it's sufficient if we say aluminum. Everybody would know this element has the number of proton as 13. But if you want to really go into the detail of is different isotope, this is going to be 27. Okay, and it's sufficient also to write down only aluminum with the left superscript 27. Okay, we all made a subscript Z because the chemical symbol can always be used to determine that if you use aluminum, it's fine. Anybody? Oh, what happened? Anybody would refer themselves to the Z equal to 13. Okay, it's proton element. Okay. We often omit the subscript set. Okay, for simplicity, if you work with that every day, you can remember that. As far as for me too, when I'm from electrical engineering, I cannot remember that at all. I don't work in chemical engineering. I'm sorry for that. I cannot remember. The nuclei of all atoms of a particular element must contain the same number of protons. Okay, that's very distinct. Okay, that's the identity of the element of any element, but may contain different numbers of neutrons. Okay, and that's the rarity in nature. But the rarity in nature, but it's gonna bring something different. Many properties are the same. Okay, for different for various isotopes of an element, you may have something similar or not. I'm not sure. You may have something shared between different elements, but something that is different is only the number of neutrons inside the nucleus. It's better if we consider the example, for example, carbon 11-6, right? We know that carbon has the number of proton as 6, right? And carbon has 6 protons inside the nucleus. But for different nuclei, they could have either 11 nucleons, okay, 5 neutrons and 6 protons for carbon 11. The carbon 12 has both 6 protons and 6 neutrons, and this is the fundamental isotope that could be found in their life in nature, which is about 98.8.9. Okay, it's almost 100% in nature. And carbon 13-6, carbon 13, which is another isotope, okay, apart from carbon 12 and carbon 11. This could be found only 1.1% in nature. All right. And what else? The next one is a bigger carbon, and is used in carbon dating. Is I don't know, maybe the last isotope of carbon. It includes even more neutron. It has 8 neutrons and 6 protons. This one has 7 neutrons and 6 protons. You could see that this one, carbon 11 and carbon 14 are quite rare. Okay, it's very hard to find carbon 14, and carbon 14 would stay usually with carbon 12. Okay, the hydrogen has the 3 isotopes. Okay, this is one of the basic elements you need to know. Its isotopes. It's called, of course, the first one that is used in Bohr model is the simplest atom, hydrogen, and hydrogen 2-1. Okay, let's draw. Okay, I have already drawn, right? This is hydrogen. Okay, you have electron around it. This is hydrogen. And the next one is deuterium. You have one proton and another proton. You have another electron. You have another electron, and electron is moving, right? This one is also moving. Oh, I'm sorry for that. My God, I'm stupid. This is already helium. No. Oh my God, it's completely wrong. I'm sorry for that. We have only a single electron. Yes, single electron. And this one is not proton. This one is neutron. Okay, neutron later in. It is neutron, and electron just move around it. And this is called deuterium. ผมอาจจะออกเสียงแบบเยอรมันนะครับ Okay, deuterium. I don't know how to pronounce it in English. Once you have more, this is one proton, and if you have another neutron, that's 3 nucleons inside nucleus, and you still have only single moving electron. This one is called tritium. Okay, tritium. Okay, you could see that the left subscript number one, okay, will be the same. Okay, if this one changes, the element is going to be changes too, right? And the difference is only the atomic mass, which is 2, and because 2 is equal to the number of particles in the nucleus. Okay, 2 nucleons, and here 3, because we have 3 nucleons, proton and neutron staying together in the nucleus. Okay, in nuclear physics, a convenient unit of length. Okay, now we have finished nuclear physics, which is the introduction to this chapter. You would be familiar with this knowledge first, this term first, and then we go to the first subtopic, which is nucleus size. Okay, in nuclear physics, okay, the scale is different. Okay, you know that the most appropriate scale of the distance or the length for the atom is angstrom, right? It's 10⁻²⁰. That's angstrom. But for the nucleus, it's even smaller than the atom, the atomic size. Well, it's not appropriate to talk about that in angstrom anymore. Okay, they use another scale, another prefix unit is called Femto Meter. Okay, it's I suppose that it is I'm supposed that it's derived from the word Fermi. You know Fermi, right? It's or people they may call it Fermi, Enrico Fermi, right? It's the surname of one of the famous physicists, okay, in the world. He talks about quantum physics. He considered also the nucleus and nuclear physics. Okay, it's written by F and M, right? It's not frequency modulation in the electromagnetic wave chapter. No, it's small f and small m. okay, not capital one. Capital one will be referred to frequency modulation, which is one kind of radio wave. Okay, it's small f and m, which stand for Femto Meter. Okay, or Fermi, simply speaking, Fermi. Okay, Fermi is much smaller than 10 raised to -15. Okay, angstrom is 10 raised to -10, right? That's the angstrom. For Fermi, it's 10 to -15, and several experimentalists review that most nuclei are approximately spherical and have an average radius that is given by equal to R0 A to 1/3. Okay, that's the third 3 square root of A, which is the atomic number, right? A is atomic number, right? Oh no, A is the atomic mass. Okay. Of course, if you have more neutron, the radius is going to be bigger. Okay. Yes. It might not be exactly spherical, but because, you know, of course, if you have a single proton like in hydrogen, it should be sphere because proton seems to be sphere, right? But if you have deuterium, you have one proton, you have one neutron. How could we say this is the spherical shape? It's two spheres. Okay, they are two spheres, and yeah. Anyway, the physicists or the experimentalists assume that this is considered as a spherical shape. Okay, and yeah, in order to of course, one of the quantity that could well describe the spherical the sphere is the radius of that sphere, right? Yes, and yeah, they try to get the information of the sphere of the sphere radius, and sphere radius is equal to R0 A10 A to 1/3 A to the third, right? And yes, it's R0 is the constant, which is derived, which is in the order of 10 to the 15 of Femto Meter, and that's the most appropriate scale for the nucleus size. Okay, since the volume of the sphere, any sphere, right, in mathematics or in physics, is 4/3 pi r to phi r cubic, right, to the power of 3. R23, and yes, once you substitute this one, R0 A 1/3 to this location, okay, equal to R0 A 1 A to the third. Yes, of course, with the power of 3, you would have R0 cubic to the 3, and A with the power of 3 is going to remain only A. You have A right here. 4/3 pi remains the same, right? It means that the volume of the nucleus is linear to the mass number A. All right, that's, yeah, the sentence says that the sphere proportional is linearly proportional to A. Okay, it's only a constant, and that constant is this one. This is the constant for this proportionality, right? Iron usually has A equal to 15. Okay, the mass number, sorry, 15, not 50, 56. Okay, iron or ferrite, okay, Fe ferrite means iron. It has a mass number as 56, but actually it's not it's not 56, it's in atomic mass unit, it's going to be 55.845. And 26 is the atomic number, right? Its number of proton is 26. They have 26 proton in the nucleus. And yeah, that seems to be the most strongest, the most dense. Oh no, the bonding force inside the nucleus seems to be very, very, very high. You will see it later. Ferrite is something like this. It's known in English as iron. It's a transition metals. Okay, the metal that can be transformed, can be changed. Okay, find the radius, the approximate mass, and the approximate density. And approximate density is going to be a good indicator for us to determine whether that element is hot or not. Okay, the radius, approximate mass, and approximate density of the iron nucleus. And yes, radius is Fe equal to R0 A to the third, right? R0 is 1/2 of 1.2 femto meter, and 56, right? 56 is the atomic number of atomic mass of ferrite of iron. So you substitute this one into this expression, okay, to R equal to R0 A1 by A to the third. All right, you get this one. Okay, after you use your calculator. Okay, after you use your calculator, and you get 4.6 femtometer approximately. Okay, and neglecting the small difference in mass between protons and neutrons. Okay, because actually, if you go into the detail, the protons and neutrons has different mass. Okay, and the total mass M of the iron could be found from 56 times 1.67. Okay, the number, the digit here of the third digit after the decimal point is different for proton and neutron, but once you say 1.67, okay, they will be valid for both particles, for both protons and neutrons. 1.67 times 10 to negative 27, and that's the mass of the nucleons in the approximation way. Okay, 56 times this one is 9.352. 10 to negative 27 is replaced by 1, right? Okay, it's added by 1. And the volume is this one, okay? The volume could be computed from this expression, from the radius, right? Right here. You could do it in this way, right? Or you just simply use this formula, or you can also use to the third to the 3 for 4/3 pi r to the 3 of ferrite. Anyway, in both ways, you will get the volume somehow. It is 4 times 10 to 43, which is very, very small. That's the volume of the volume in spherical shape of the nucleus of ferrite or the iron. And in order to get the density, we divide the mass of the ferrite by the volume of that ferrite. And it's going to remain 2.3 times 10 to 17. You could see here that the density of the water, okay, if you carry the water, you could feel it's quite heavy, right? If you carry a bottle of water like 1.2 liter, it's quite heavy, 1.2 kilogram, right? And the density of the water is that for 1 cubic meter, it's gonna have you would have 1,000 kilograms. Okay, 1 ton in 1 cubic meter. You have 1 ton, which is 10 to the 3, right? 10 to the 3 of 10 to 3 of kilogram, right? 10 with the power of 3. But this one, the ferrite, the iron, the density is on the order of 10 to 17. My God, it's much stronger than heavier than the mass of water, right? Mass of water is 10 to 3, but this one is, let me say, the rho of H2O is only 10 to the 3 kilogram per cubic meter, but this one is 10 to 17. My God, is much heavier than ferrite. In the nucleus, the protons attract each other via the nuclear force, and at the same time, they repel each other through the Coulomb force. Okay, yeah, protons staying together. Okay, protons stay together by using the nuclear force, but because they have the same positive charge, they're gonna repel each other. Okay, repelling force is not repulsive force. Okay, they are gonna repel each other. Okay, they try to put each other, and that's the negative thing. Yeah, nuclear force. What is the nuclear force? Nuclear force is an active force. Is an attractive force that acts between all nuclear particles. Nuclear force doesn't exist for only proton and proton, but also proton to neutron and neutron to neutron. Okay, any particles inside the nucleus would have the nuclear force, which is a kind of attractive force. And the interaction, this is the idea suggested by the physicists. Okay, the interaction are approximately the same. Okay, there are 2 force types in the nuclei, such as the weak nuclear force and strong nuclear force. The strong nuclear force is about 10 times more 100 times more attractive than the repulsive electromagnetic force. Okay, this is the Cauchy force by what is that? Repulsive. Let me check. They try to repel each other, right? The repulsive force. Yes. Yes, repulsive means repelling too, right? Okay, that's the kind of repelling force, and this is the strong nuclear force. This is the weak nuclear force. Okay, yes, nuclear force are short ranges. Okay, and they fall down when the nucleons are separated by a few femtometers. Only few femtometers. It's gonna reduce it. Okay, automatically. Nuclear force becomes extremely repulsive if the nucleons gets too close. If you try to put the nucleons to be very close to each other, the repulsive force is gonna be strong. Okay, and yeah. Yes. Okay, we have already we reached the, okay, we passed the nuclear side, we arrive at the nuclear force, right? And the nuclear force could be discussed also in this figure. Let's see, what is that? This is the plot of the number of protons along the x-axis. Okay, the number of protons increases along the x-axis. And of course, when you change the proton number, it means you change the elements on the periodic table. And here is the number of neutron. Okay, yeah. Yeah, the number of protons versus the number of neutrons in a nucleus. What is that? First, we consider the case, this line. Okay, this is the case when it is a straight line. This is the case when n equal to z. It's like you have the equation. This is x. This is y axis, and it means y equal to x. Okay, and that's the same thing. You have this plot. That's the straight line of y equal to x. But because our y is n, right? N equal to z. Atomic proton. N equal to z, right? N equal to z. That's the same kind of straight line. Y equal to x. Okay, it's in 45-degree tangential. Yeah. It could happen that the nucleus is the nucleus has any number of neutrons, right? But at least it should, the number of proton and the number of neutrons should be very close to the number of neutrons, and that's the case. These are the example of the existing nuclei that the scientists could have found that have found on Earth. Okay, is in the gray area, but the black dot one, the black dot one is the stable nuclei, black dots. Okay, like in the narrow band called the line of stability. Okay, this one. And the shade, the gray one, is the non-stable nuclei, and it's called radioactive nuclei. Okay, these nuclei will transfer, will change to another type of elements later. Okay, but anyway, from what you could see here is that okay, it can happen that the number of neutrons is less than, okay, under this line, under this straight line n equal to z. It could happen at the beginning that the number of neutrons could be less than the number of protons, but it's not stable. Okay, the stable elements or stable nuclei would be the one that have the ones that have more neutrons than protons inside the nuclei. Okay, and that you could see here that the black dot one is above this line. Okay, and what is the reason for that? The reason is that once you have more neutrons, you could have more nuclear force, and the nuclear force is the attractive force, right? The attractive force is good because it's gonna try to keep so many neutrons together, right? It's not the bad thing, right? The bad thing is the repulsive force, which is caused by Coulomb force, and that will happen if you have the same type of charges. Okay, like you have more protons, you have more positive charges, and they are going to repel each other. Okay, and that's the thing that happens. Okay, that's the result from book number 1, and here is the result from book number 2. From book number 2, they also consider the case of n equal to 20, n equal to 40, 60, 18, 190, blah, 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 right? And as the mass number A increases, stable nuclei have an increasing ratio of neutron to protons. Okay, this one is called Segre chart showing neutron number and proton number for stable nuclei. Stable nuclei means the black dot one here. Okay, the black dots here represent the stable. Okay, if you leave these nuclei in nature, they will not change themselves to smaller atoms. Okay, we will just say like that. But the other atoms in this gray region, they will transform themselves to a smaller atoms, to smaller nuclei. Okay. Once they say nuclei, you may notice this one, nuclei. Okay, nuclei mean stable nuclei. Okay, nuclei is the general word for the plural form of nucleus. Okay, light nuclei are more stable if they contain equal numbers of protons and neutrons, and there is no stable nuclei. You could say nuclei is used for the case when the nuclei is stable. There is no stable nuclei for A equal to 5 and A equal to 8. You know the reason why? Because the stable atomic unit is the atomic number is 4. A equal to 4 is a very stable nucleus because you have 1 proton and 1 neutron and 1 neutron. So this is the good combination of the nucleus. And what is that? It is actually the nucleus of what? Nucleus of, what is that? It is, of course, you would have 4 electrons around this. What? You would have 4 electrons around this, right? You would see, right? This corresponds to, what is that? The number of nucleons is 4 because we have 4 particles, and the number of protons, we have 2 charges here. So it's 2. What is that? It is, yes, it is helium. Helium-42. The nucleus of helium-42 is very, very strong. Okay. And because it is very strong, it's a noble gas. It has no chemical action or reaction to any other chemical agents. Because it's very strong, it's very, very stable. Okay, but good combination. Okay, good. Only a single repulsive force, but there are 4. I don't know, 4 factorial. 3 factorial, right? 6 attractive forces here. Right, so 6 versus 1, so it's quite strong. Okay, A equal to 5 will not be strong. Okay, if you put more proton into this one, okay, they are gonna have no pair. Okay, it will have no pair, and finally this proton is gonna go away. Okay, and that's why when A equal to 5 is not stable. Okay, once you have 2 protons and 1 neutron here, and you add another proton, this proton will go away finally because he doesn't have any pair to that. Okay, and for another case for A equal to 8, you have this one and this one and neutron. Okay, this is the nucleus of A equal to 8, and finally, this one is gonna be split to form up a new element of helium. This one is gonna split from each other to form up another helium nucleus. Okay, and that's why A equal to 5 and A equal to 8 are not stable elements. Okay, a nucleus, a pair of protons and a pair of neutrons. That's the stable nucleus. And because they are very, very stable, the helium-42 nucleus, even we throw away 2 electrons, it's going to be strong. It's going to be the nucleus is still strong. Okay, and yeah, it can move as a single object because it is the alpha particle, right? Yeah, helium-42 is the alpha particle nucleus. Okay, the time is over right now, right? 10:10 is your time for breaking. We need to leave 20 minutes for you to have a break. See you on, today is Friday, right? See you next week. And the homework, right? The homework for you this week would be this one. The nuclear size, okay, homework is the nuclear size homework of, I don't know, homework, 7 homework or the 8 homework, I'm not sure. Let's see what happens. Yes, it's classwork. It's yeah, it's the 8 homework for us this week. So the 8 homework assignment, right? It's 06.0 1.20 22 8. Eight homework is the nucleus size. Nucleus size homework 8. Homework on 207.01.2022. It's 7. It's not 6. 7. Nucleus size equal to 0 A 1/3. Oh, what happened? Okay. Yes. Okay. The next formula is V sphere, right? V sphere equal to 4/3 pi 4/3 pi and 0 to 3 times C. Okay, and that's the homework. It's 1 point. 1 point in due date is going to be next. Today is 7, next Friday, and 9 a.m. Yes, nucleus size. Okay, M604.นะครับก็สามารถเลือกเลยได้นะครับ M604K is the time is over right now. I just assign the homework, otherwise it's gonna be forgotten. The strategy is one, and let's talk about what appears in the classroom, right? In the classroom we have Pavit Tanya. Let's make smaller. Pavit. Okay. And then we have Kapsidit Pichetpong. And here we have Brad Chat. All right. Test 1, 2, 3. Test 1, 2, 3. Okay, เสียงใช้ได้ Test 1, 2, 3. Capture ยังไม่เข้า 10, right? Where is that?อีกแล้วครับมาถูกโทรมา Need to make sure this is the 19. Oh, 19, the one from oh yeah. Mhm. So M605. Defect mass and this one, right? Okay. Yes. กันตะพลเดี๋ยวกันตะพลห้องไหนอ่ะกันตะพลมาด้วยครับร้อยครับว่าเราจบที่กิติพันธ์แล้วนะครับกันตะพลก็กันตะพลกันตะพลด้วยนะครับ604นะครับกันตะพล2นี่บทjust use that. That's the case. Okay. M605 already appeared, but I'm waiting for the result of counterpoint from M604. Hey, don't worry about it. Okay. เวลาสิทธิ์มานะครับพี่เชษพงศ์604นะธนทรมาแล้วนะครับมีใครจะเข้ามาที่ซูมไหมครับผมดูนะโอเคครับจะได้กดรับให้นะครับใครอยากเข้าที่ซูมนะครับกันทพลนะครับ alright anyone want to join that right yes I'm waiting for a result but not yet ไม่ครับนะมันเครื่องอาจจะช้านะครับเพราะรันหลายอย่าง anyway yes okay I don't know what okay let's know when no one want to join the Zoom, right? And get back to I will get back. When maybe internet problem. I will get back to the. We have to use C3, I think. Or NTMax. In this case. Okay. Yes, this is the section for M605. You have already considered so many things, right? Energy buying and so on, right? Deuterium energy binding, right? That's what you have seen before. Yes, of course. It's M605, and I need to wait for the result for catapult. Okay. Let's talk about this table, right? We have already considered this one, right? This is the energy binding calculation, nucleus of deuterium, right? Deuterium is in this table. Deuterium is the case when deuterium is the case when you have one proton and one neutron, and you have a single electron moving around. Okay. Usually, in the typical hydrogen, you should have only a single, what is that? Single proton, right? There will be no neutron at all. But yeah, once you have a single electron moving like this, then it means you have another isotope of the hydrogen. It's called deuterium. Deuterium is the case here when your atomic number set is 1 and the number of neutrons is 1. It's known as in atomic symbol, you would say it's 1, 2. Hydrogen is 1, 1. Okay, and the mass number is over here, right? The number 2. And the mass number doesn't mean that the atom has 2 atomic mass units. The atomic mass is actually 2.014101. Okay, you have to use this number instead of that. And yes, of course, the energy binding is we have to first calculate the excess mass, right? The number of proton, because we have a single proton here, set is number 1. Mass of proton is 1.0. This is what you have seen before, right? This one number is 1.00727, right? 00727 and 1.00866. That's the mass of neutron. You're gonna use that. You need to use that value in yes, it's right here, and because we have a single piece of neutron in the deuterium, because we have a single particle of the deuterium, and you have atomic mass of the deuterium, which is 2.0140101 or 102. It's a little bit variation. And yes. โอเคปานทรครับ605นะแล้วก็ตรงนี้ไล่มาตั้งแต่ธนกรถิ่นธรรมครับ605โอเคแล้ววิพลนะครับช่วยเขียนหมายเลข20นะแล้ววิพลเพราะว่ามันจะได้ตรงกับตารางไม่งั้นผมต้องมานั่งจำคุณอยู่คนเดียวครับแล้ววิพลเข้าใจอยู่ว่าเลขที่เดิมคุณ21นะครับแต่ว่าในวิชาฟิสิกส์นี้นะครับขอความร่วมมือช่วยเขียน เลข20ให้หน่อยนะครับแล้วพี่พลนะครับคนอื่นเขายังเปลี่ยนได้เลยนะครับโอเคไหมไม่งั้นคุณก็จะไปซ้ำกับวาลินนะครับโอเคไหมเดี๋ยวผมก็เช็คคุณไม่เจอบางทีทำคุณขาดไปอะไรอย่างเงี้ย Okay, you just make the subtraction. This is the mass from elementary particle, and this is the mass from the actual mass in the nucleus. And you could see the excess mass, the mass defect, okay, the mass that is lost. Okay, and the resulting delta M is multiplied by the conversion EMC square, right? This is the amount you got from the EMC square by Albert Einstein. And yes, E M, right? E is over here. M is the mass of one atomic mass unit. Okay, whatever particle, we use this value, and this is the speed of the light. And once we scale a little bit by 1 million, we have 931 mega electron volts, and yeah, you get one atomic mass unit like that. And yes, the excess mass is converted to the energy, and this energy is called energy binding. It's equal to 2.224 mega electron volt, and that's the energy binding you could get easily. Okay, you don't have to start from EMC square. Okay, just use this one, 931. It's very useful. It's very important. All right, and yes, we're going to use that M604. Gonna put this right here. All right. Okay, 931, and once you convert it to 931, you get this value 2.224 mega electron volt. All right, that's the energy binding. This is the appropriate scale. Okay, you could see the result is only 2. Okay, for a bigger atom, you may have helium. Helium start from 2. Helium, another isotope with 2 neutrons. I don't know, they don't have a new name at all, right? It's called helium. But with this one, you have 4 nucleons. You have the 4.002603, and lithium, right? Lithium with 4 neutrons, lithium with 3 neutrons. Beryllium doesn't have 4 neutrons at all, right? They have only 5 neutrons. Boron has 5 neutrons, boron with 6 neutrons, okay, and blah, blah, okay. And for oxygen is number 8, right? Atomic number is 8. When the number of neutrons is 8, you get 15.99, and when the oxygen is 8, when the atomic number is 8 and number of neutrons is 10, you have 18. The nitrogen 7, nitrogen 8, nitrogen 14, nitrogen 15, okay, has different value of atomic mass too. For the carbon 12, okay, let's talk about it. Carbon 12. Carbon 12 is the stable one. One stable element of the system, right? The result here is what you may observe from this table. Carbon 12 with this one, right? Okay, 6 plus 6 is 12, and the atomic mass is exactly 12 because this is the standard element that is used to measure or or measure others to use as the reference for other elements to measure the mass in atomic mass in U. Okay. So mass defect, total binding energy, and binding energy per nucleon, right? That's what we need to consider. Okay. Mass defect is the number of is the difference between the mass of each of our nucleons, right? You have 6 proton. You have 6 proton. You have 6 neutron. You have 6 neutron too, right? And you have to multiply 6 to the mass of one single proton. You have to multiply the mass of single neutron by 6, and you get that value. And after that, you have to subtract by 12. Okay, 12 is the result from this table. Okay, 12 is 12 comes from this one, not this one. Okay, 12 comes from atomic mass, not the mass number. Okay, 12.07. That's why we have a 12 units here. Okay, and after that, you put it into the calculator, right? Once you put it into the calculator, you get this one. Okay, which is very, very tiny. It's 0.09894 unit. And yes, 9894 units, and you convert it, right? You need to convert it to the total binding energy, and yeah, it's 93 delta M times C square, right? It's 931.5 mega electron volt per unit. Okay, and you have units here. And after that, you could get the result from the calculator. It's 92.16261. Okay, 92.16261 mega electron volt, which is quite large actually. For the deuterium, you have only 2 mega electron volt, but this one is quite large. You could see that for the bigger nucleus, for the bigger atom, you need to have more binding energy. The energy that tries to attract several nucleons to stay together in the nucleus. Okay, because you have more nucleons, you have more particles in the nucleus. You need to have more energy too to combine them to stay together. Okay, to combine them into a single piece. And this is the total. That's why they say total binding energy. The next quantity is the binding energy per nucleon. So you have to divide the total binding energy by the number of nucleons you have in carbon-12. Of course, we have proton and proton. We have proton, proton, and neutron, 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 neutron. Okay, 6 pieces of each. So you have to divide the binding energy per this one. Okay, and you could see that once you divide EB by A, is called binding energy per nucleon. Binding energy per nucleon will be 92, the resulting number divided by 12. And after you put it into the calculator, you get 7.68 mega electron volt per nucleon. And this one, what is that? You have 1 proton, 1 neutron, right? Deuterium. And if you want to consider binding energy per nucleon, you have to divide this number by number 2, right? There are two nucleons, so you have to divide this number by 2. You get 1.112 mega electron volt per nucleon. Okay, it's approximately, if we say binding energy per nucleon, right? It's going to be 1.112 mega electron volt per nucleon, right? And yeah, that's the result you could get. This is if you compare it, 1.112 is much less than this one. Okay, so the carbon 12 has more binding energy per nucleon. Okay, so what is the meaning to that? Any case, if you have more binding energy per nucleon, it means your nucleus staying together with more strength. Okay, it's your nucleus is strong, right? Okay, yeah, that's the thing you would have here. For example, you have 1.112, right? As I told you here, as we have found 1.112, and if you plot it, it's going to be here somehow here for the deuterium. Okay, for the hydrogen, we don't have binding energy at all. Okay, we wouldn't have binding energy at all because we have only a single proton. Okay, proton has nothing to do with other, has no interaction with other element at all. So the first one is the deuterium. So it's only 1.112. It's very low. And for carbon 12, where is carbon? Carbon is 6, right? Carbon is over here, which is 7.6. Okay, it's carbon is right here. It's less than 8, but it's a little bit bigger. 7, bigger than number 7. Carbon is right here. Okay, and carbon is quite strong. And sodium is also strong. If you go further, it's going to be choline, ferrite, which is iron, and nickel is the strongest one. The region of greatest binding energy per nucleon is shown by the 10 band. Okay, around this area, 56, 62, and 72. Okay, from 56 until 72, this is the heavy metal. 57, 58, blah blah blah. We have different elements. 56 until 72. Let's get back to the 56 till 72, right? 56 is right here. Oh, there. Right. Where is that? That's 56 is the atomic mass, right? But ferrite is only what is that? Ferrite is, the iron is only 26, so 26 to something like that. To germanium. Iron to germanium, where is that? Iron 26, right here. Okay. Not manganese. Iron to germanium. Where is GE? Where is GE? Also here. Okay. Ferrite to germanium. Okay, it's around here. This is the range of the metal that has very high ferrite to germanium, very high binding energy per nucleon. Okay, in this region, in the elementary, in the periodic table, for both for those elements. Okay, from this figure here in this 10 band. Okay, if you go further, it's going to be weaker. Okay, the binding energy per nucleon is lower until you reach like uranium, radium, lead, right? Gold or silver, something like that. Okay, Yeah, this is the figure of binding energy per nucleon versus with respect to the mass number A. Okay, it's the total number of nucleons inside the nucleus. And this is another figure. This is taken from book number 1. It is shown in figure. Yes, we have 1.112 for the deuterium. We have 7.68 for the carbon 12. For helium, even helium, they have quite high binding energy per nucleon. Yeah, and then we have the highest one as the nickel, right? The curve reaches a peak about 8.8, and what we have got here is 7.6. Okay, 1.2 more mega electron volt for nickel, and A equal to 62. This is the nickel 28. Okay, when the number of protons of that element is 28, we call nickel. The number of remaining nucleon is the number of the neutrons, right, which is 34. Well, they have 34 neutrons. Okay, 28 protons and 34 neutrons. Okay, the spike at A equal to 4 shows the unusual stability of helium. Okay, you know that if once you have when you have 2 neutrons, 2 protons, you get helium-42, right? And because of the high amounts here, it means that the helium-42 actually has a very stable nucleus. Okay, helium-42 has a very stable nucleus because the binding energy here is quite high. It's 7. Okay, compared to maximum is 8.8. Okay, and carbon too. Carbon has also a stable nucleus. Carbon 12-6. Okay, now we reach the next topic, radioactivity, and I have to prepare more slides later because we're gonna reach the end soon. In 1896, Becquerel accidentally discovered that the uranium salt crystal emits an invisible radium that can darken photographic plate if the plate is covered by exclude light. The spontaneous emission of radiation is also called radioactivity. Okay, the Becquerel is the first person who considered the radioactivity. He's a pioneer, but one more important person is this pair. Okay, this spouse, Marie Curie and Pierre Curie. Okay, Marie Curie just go to the university and work in a research group, and Pierre Curie is also a researcher. Then he is a son of a professor, and they work together. They met each other, and they got married to each other, and they are a couple in reported the discovery of 2 previous unknown elements, both of which were radioactive. Both are polonium and radium. Where is that polonium? Polonium, PO, right? Polonium, where is that? PO, polonium. Right here, okay. Polonium is metalloid. Polonium and radium. Polonium and radium. Polonium is right here. Radium. Where is that? This is radon. Okay, radon has also a role in our lecture. We will talk about radium. Okay, radium is right here. Polonium 84 and radium is 88. Okay, and the atomic number is 88. Okay, 84 and 88. Yes, is 84 and 88. Okay. Subsequent experiments by other scientists show that other substances were also radioactive, not only polonium and radium are the two elements that molecularly and empirically have discovered the radioactivity from these two elements, but many researchers, many scientists have found also radioactivity from other elements. Okay, not only that. There are 3 types of radiation that can be emitted by a radioactive substance. The first one is alpha particle, right? This might be the one that we have discussed before. Alpha particle is helium-42, but alpha particle is the helium that has no more electron, and when we don't have electron, because helium has 2 protons, right? They have 2 electrons, but when its 2 electrons are away, we're going to say it's ion, or it's only nucleus, and 2 plus here means the 2 electrons are missing in chemical formula, and that barely penetrate the sheet of paper. And beta particle is the emitted particle that has either electrons or positrons. Can penetrate a few millimeters of aluminum. Gamma ray is the emitted rays of, and it has high energy photons. It can penetrate several centimeters of lead. Okay, yes, we can see gamma, and we can see that the gamma is quite harmful because it can penetrate. You would have ever heard that the nuclear power plant, okay, the power plant that generate electricity from chemical reaction from the nucleus. Once they were explode, the ray the rays that are most dangerous for human would be these one, gamma rays, because it can escape the protection of several walls that made by heavy metal, for example, lead and so on, right? Because it has ability to penetrate several centimeters of lead. Once the density and the intensity of the gamma ray is high, that is also dangerous. And here, this is what here is what we have already discussed. The alpha particle will go up because it is a positive charge. The electron, okay, the beta ray that has electron as the outcome will go down, okay, because it's in the opposite way as the positive charge. But if you have the positron out of this chemical reaction, which is a kind of beta particle, the positron is going to move in the same way as the alpha particle too. Okay, this is the mixture of sources that emits alpha, beta, and gamma ray. It can happen that a radioactive element that could produce either not even, that could produce 3 kinds of rays or particles. Okay, from 2,500 nuclei or nuclei, only 300 are stable. Okay, and the remaining one decay by emitting. Okay, so only 300 will be stable. So 2,200 nuclei are non-stable, are not stable, and the 2,200 types of nucleus will decay. Okay, will change themselves into a smaller one. Okay, will be split it into a smaller one. From this process, from the splitting process, it's going to emit the particles and transform themselves into other nuclei, which also might be unstable too. Okay, even the result could be also unstable, and it's going to broken into a smaller nucleus again. Okay, nucleus is unstable if it's too big. For example, when Z is greater than 83. Okay, the element greater than 83. What is that? 83 is bismuth. Okay, like polonium. This one. Okay, radon. Blah blah blah. This kind of elements which is greater than 83, okay, 84, 89, 90, blah blah blah. Okay, thorium. All of these are not stable. Okay, they are unstable, and they are gonna be broken into a smaller nuclei. Okay, to smaller nuclei. What is that? If it's too big, okay, if neutron-proton ratio is wrong too, right? Or when the number of nucleons is greater than 209, which is very, very big, okay? When the combination of neutrons and protons is greater than 209, my God, is very big, and the nuclei will be split into small one, okay? And that's the case similar to atoms and molecules. Nuclei have internal motion, okay? Of course, you have many particles packed into a group, right? You have many particles like crystal, but they don't have a contact to each other, right? During this in this area, there is some space, and they're gonna vibrate, and with the vibration, you could have the energy in the internal motion could happen, and set up allow energy level, including ground state and exciting state, could take place. Okay, it depends on solid state. Okay, if it vibrates so much, it's gonna have more energy. Okay, yeah. And if they want to be in the ground state, they will release the energy, as same as the electron, right? In the higher orbit to lower energy state, they're gonna limit the photon. Okay, it's the same thing here, but the nucleons inside the nucleus that don't move in a circular way like electron. Due to the great strength of the nuclear interactions, excitation energies of the nuclei are typically on the order of 1 mega electron volt. Okay, if you wanna make them vibrating, okay, you wanna vibrate them, you need to put the energy on the order of 1 mega electron volt. Okay, compared to few electron volt in atomic energy levels. For electron, you need to put a few electron volts for atomic energy levels. The nucleus always remains in its ground state. It's gonna be in the ground state, okay, by releasing the energy before. Okay, in phase in the excited state, a nucleus can decay to the ground state, and the emission of one or more photon, namely gamma ray or photon. Okay, the nucleus, as I told you, they're gonna release the energy somehow, and the way to release energy is that the nucleus will produce or generate the photon in terms of gamma rays of photon gamma rays, and the energy of that emitted ray is on the order of mega electron volt. Okay, you could see that which one is greater than each other, which one is It's higher. This is 1 million electron volt. You could see this is the high energy if you want to excite the nucleus. Okay, but for atomic level, you are on the order of 13.6, blah blah blah, right? 13.7 or 8. But this one is million. You could see that the nuclear bomb has around 1 million more energy than the energy caused by electron. That's why the human has used this interaction to get the energy. And the energy, if you use the energy in the wrong way, that could be harmful to everyone, right? But if you use it in a good way, like in the nuclear power plant, right? You generate the electricity from the uranium, only a few gram or few kilogram. You get a very, very high amount of energy. That's in a good way. Yes, the emitted ray, it will be also in the mega electron volt scale. Okay, it's quite high. The disintegration of the nuclei that do not meet the stability requirements is called radioactivity. Okay, now we start with the origin of radioactivity. It means the case when big nucleus is split into small one because of its instability. Okay, and that process is called radioactivity. Okay, the first thing, we arrive at the decay rate. That's the first subtopic in radioactivity. Please let me go to the toilet for a while. ขออนุญาตเข้าห้องน้ำแป๊บนึงครับ Okay, I'm sorry for that. Now we will start with the calculation in radioactivity, right? The first thing we need to know is the decay rates, which is the fundamental term to to calculate something in the radioactivity process. Yes, observation has shown that physics is not far from experiment. Okay, so everything should be done in the same simultaneously with laboratory, with experiment, and so on. Observation has shown that if a radioactive sample contains n radioactive nuclei at some instant, okay, for example, we have n radioactive nuclei. The number of nuclei delta n, okay, that decay in a small time interval delta t is proportional to n. Okay, so this is the number at the beginning. Okay, at the beginning, the number of nuclei at the beginning, and the number of nuclei that disappear per time is called delta n by delta t, and it's going to be proportional to the number of nuclei at the beginning. It's called proportionality, right? Linear proportionality, but linear in a different way, in reduction way. Okay, so the rate of changing, the rate of change is negative, so the number of nuclei decreases in this case. And from the proportionality, if you want to write down the equality, you need to have the constant, right? Of course, negative means the number of nuclei reduces, right? But there should be a constant, and that constant is called lambda. Lambda is the decay constant. Okay, yeah, actually it's K, right? But it's known as the lambda for this specific environment. It's called decay constant. Okay, the decay rate or activity is called activity rate too, right? Is the amount of the absolute rate, or the magnitude of this one. Okay, so we throw away the negative, right? The rate of change in absolute value is this one. Okay, lambda and n. Okay, you could see that the rate of change, the rate of reduction, actually, okay, the activity decay rate, a rate of reduction depends on the constant K2, right? And depends on the initial amount of your nuclei. Okay, it's not the number of nucleon, it's number of nuclei, right? Which is the plural form of nucleus. If you say nucleon, it means the number of subatomic particles inside the nucleus, but it's not the number of subatomic particle in nucleus. But anyway, you could find the relationship between nuclei and nucleons, right? If you know exactly what the element is. Okay, let's go further. The rate of change, the decay rate, could be explained in terms of either Curie. Okay, 1 Curie means 1 Curie means 3.7 10 to 10 decays per second. And in SI system, it's going to be called becquerel. Okay, Curie is the surname by Marie and Pierre, right? Curie is the surname by Marie Curie and Pierre Curie, but becquerel, okay, becquerel is the pioneer person, right? Is the pioneer. So we would use his surname as the SI unit, and it's called becquerel. 1 becquerel is 1 decay per second. Okay, only elements, okay, 1 decay per second, but this one is, I think, more appropriate one is 3.7 10 to 10 decays per second. Okay. When the time interval tends to 0, when we take the limit to 0, we get the differential, right? Instead of the difference delta, yes, we have the differential version, and that's going to be still the same. That remains the same as negative lambda and n. Okay, and we're going to solve this problem in calculus form. I hope that you may have ever heard you may have ever seen the calculus the idea of calculus before, right? So in differential way or integral way, right? Yes. Let's go further. See what happened with this, right? When we move into the left hand side, in delta t to the right hand side, we're going to get dn by n, and is equal to minus lambda dt, and we obtain, and if we make the integration for both of these, right, like this, integration dn by n in minus lambda integration dt. Of course, you will get t, but you would have a constant c also. This one is ln n, right? It's ln. You would get also lambda t plus c. C is the constant caused by the indefinite integration, right? It's indefinite integration because we don't have limit, lower limit and upper limit at both sides at all. And ln x is the natural logarithms function of the variable x. So we have n here, so it's natural logarithm. And if we don't want to express n in terms of natural logarithm, we need to take the exponential to both sides, right? We're going to have ln n equal e minus lambda t plus c. Okay, and this will split into e minus lambda t and e with the power of c. Okay, and e with the power of c will transform itself to n0 to get n0 from this one, and e raised to negative lambda t will stay the same, and n will happen on the left hand side because e with the power of ln n will be converted to only n. And of course, once you have n equal, let's say this is constant, right? It's n0 e minus lambda t. It's a function of t, so it's good to write down also the dependency of t right here. Okay, so nt is n0 e to negative lambda t. It's a good way, right? This is the closest form you could find the number of nuclei, okay, at a certain time. It's the result from the decay rate. This is the decay rate is r, right? R is lambda times n. That's the decay rate, the total decay rate. But if you want to find the remaining nuclei from the beginning, n0 is the amount of nuclei at time 0, right? If you put 0 here, right? If you put 0 to this question, okay, and when time equals 0, you get e minus lambda 0 times e with the power of c, the constant, and you would find that e is equal to n when the time is 0, and that's we call n0. Okay, e with the power of c is known as n0. The initial amount of nuclei at time 0 at the beginning, that's n0, but n0 will reduce with lambda, which is the constant. Is constant called decay constant. Okay, and the decay rate is the product between decay constant and the initial amount, and the number of nuclei at that time. Okay, decay rate at that time and decay constant. But if you want to find the nuclei at that time, you could find from the initial amount of nuclei with the e less to negative lambda t. Okay, N0 equal to e less to c is the initial amount of radioactive nuclei at time t0, as I told you. And e to the power of x is the exponential function of the variable x. The value of lambda for any isotope determines the rate at which that isotope will decay. Okay, isotope with large, of course, with large lambda value decay rapidly. So the resulting of nuclei is going to be much reduced if you have more lambda. If you don't understand, I would express it in this way. Nt equal N0 by e with the power of lambda t. Okay, with more lambda, you will reduce a lot this ratio. Okay, and the half-life of a radioactive substance is the time it takes for half of a given number of radioactive nuclei to decay. So half-life is not the half amount, is the time that the new radioactive nuclei reduces to the half. And if we substitute on the left-hand side as N0 by 2 or 1 by 2 of N0, and this one is called half-life, T1 by 2 is called half-life. And we solve this one, right? N0, we cancel each other from both sides of this equality, and you take the logarithm, right? Logarithm is going to be reduced. Oh, what happened? The telephone, sorry for that. Sorry,ครับ Hello ครับ Hello อ๋อวางข้างล่างเลยครับได้ครับครับขอบคุณครับ Okay, now we arrive at the one of the more important words in the story, which is called half-life, right? Decay rate, decay constant. What you have already seen, right? Yes, the half-life is the result of you take the of course N0 cancel each other. After you take the natural logarithm to both sides, you're gonna have negative ln 2 equal minus lambda and T1 by 2 and ln of E, right? And ln of E is number 1. Ln of E is equal to 1, right? And it's nothing. Negative and negative can cancel each other. And if you want to find half-life, you just move lambda to this one. You get half-life or T period of 1 by 2 is ln 2 by lambda. You get this one, okay, ln 2 by lambda, and is equal to 0.693 divided by lambda. Okay, and that's the, okay, it's quite simple, right? Ln 2, after you use the calculator, you could get the numeric version in approximation way, okay, in approximate way. And it's quite simple than this one, right? Just put the decay constant and you get the half-life, right? And that is the decay constant here. What is that? Here, lambda is the decay constant. And if you multiply it, it's going to be decay rates, right? 3 words: decay constant, decay rates, and half-life. Okay, using the concept of half-life, you could also express it in terms of half-life, n is the number of half-life. You start from n0 and 1/2. Okay, wait, what is that? Because you have this one, right? If you put t 1/2 to this one, you're gonna get okay. You have nt, right? Nt equal to n0 and e minus lambda t. Oh, sorry. Lambda t, and if you put n times of t, if you put n, oh sorry, n, oh sorry, n of n times half-life, you're gonna have n0 e minus lambda and nt 1/2, right? And you know t 1/2 is this one, ln 2 by lambda, right? So you would get minus lambda and n and ln 2 by lambda, right? Ln 2 by lambda, and of course lambda you cancel each other right here, right? And we could see that n0 is going to be e and ln 1/2, right? And here is with the power of n, right? Of course, you may also write down in right here, but this term will be only 1/2, right? So finally, you will get n0 and 1/2 with the power of n. So we get this one. Yeah. Okay. N at a certain half-life will be this one. Okay. N0 1/2 with the power of n. N is the number of half-life. It depends on how many half-life you want to observe. Okay. If you put n here as number one, you observe it from a single half-life. But if you put n as number two, you're gonna want to see the resulting amount of nuclei in two half-lives, 3, 4, and so on. Okay, n could be an integer. Could n be rational number? It's also possible. If you want to observe 1.5 half-life, it's also possible. You just replace n by 1.5, you get the resulting of the remaining nuclei after 1.5 half-life. It's also possible. The number of half-life can also be written as t by tp, the period 1/2. The time scale of this decay process ranges from a small fraction of microsecond to billions of years. So the time that you could observe the decay of several particles or several nuclei could be few seconds. Okay, for a very rapid nuclei in the nuclei that has a very low rate, low speed of decay, it could take billions of years. Okay, you may have already passed it away. Okay, but the nuclei of that element still remain almost the same. Okay, the reduction is not much. Okay, it could happen in nature. All right. Okay, we arrive at the half-life of the radioactive nucleus of this one, radium. Okay, radium 86, where is that? Radium 86, 86 is radon, sorry, I'm skipping. 88, I'm sorry, 88 radium. Radon is 86, 88 is radium, alkali earth. Okay, radon is noble gas. Okay, it's a gas. Radium is alkali earth, so it's very attractive to other chemical agents. 88, and the mass number is 226. Okay, the half-life of radioactive nucleus 226 radium 88 is 1.6 thousand, right? 10 to 3 years. So 1,600 years. That's the half-life of the radioactive nucleus of radium. So if you have 10 nuclei of radium, once the time goes by for 1,600 years, you would get only the remaining amount of radium nuclei will be 5. Okay, half of that. You get 2.5 after another 1,600 years. If a sample initially contains 3 times 10 to 16, that's the, I don't know. It's almost, it's 0.3 million such nuclei, right? Determine the initial activity in Curies. So what is activity? Activity is R, right? R from this expression is the decay rate or activity, right? Decay rate or activity is equal to absolute lambda, is lambda n only. Decay rate is lambda n. Okay, you need to find lambda n. You need to use this formula. And of course, you know the initial mass. Okay, initial activity, right? Initial activity means the n is n0, r0 initial, right? Is lambda n0, but we don't know lambda right now. We know from equation 29 that the half-life has relation to the decay constant lambda 2 by ln 2 by lambda, right? If you want to find the decay constant lambda, you need to move t period, t half, to the denominator on the right-hand side. You're going to get decay constant. Okay, decay constant. In you could explain 0 is ln 2 by t period. By t half times n, right? Times n0. Yeah, you could find the initial decay rate or the initial activity from this one. Is not so difficult. The number of radium nuclei remaining after 4.8 10 to 3 years. So if you divide it, if you divide 4.8 times 10 to 3 divided by 1.6, which is the half-life, times 10 to 3 will be 3. So it means 3 half-life. It means n equal to 3. And what is that? If you want to find the remaining nuclei, you have to use this expression. Okay, this expression. When n is equal to 3, okay, n is equal to 3 here. Yes, in order to find that, you could see in 0, 1 by 2 with the power of 3, right? Yeah, then you get the remaining radium nuclei. Okay, this from the expression. Activity at this later time, activity this or decay rate at this time. So you have to multiply radium, sorry, decay rate by lambda. So you once you get in here, you could get lambda, right? And lambda is ln 2 by t period, right? You just multiply it with n. All right. So let's solve by hand. Okay, let's solve by hand. The first one is the R0. Oh, sorry. R0 equal ln 2 by t period, t1 by 2, and times n0. And of course, you know, n0, the initial amount is 3 times 10 to 6, right? Nuclei. And t half period, t half life is 1.6 times 10 to 3 years, right? This is years. But the standard unit of the time in the SI system is แล้ววิพล VOI คืออะไร I don't understand แล้ววิพลพิมพ์ VOI มาคืออะไรแล้ววิพลช่วยพิมพ์หมายเลข20ด้วยนะครั้งหน้าครับT1 by 2 1.6 blah blah times into 3, right? You have to convert this amount to one important thing is you have to convert it to second, right? Because second is the standard scale in the SI system, right? 1.6 times 10 to 3 times how many days in 1 year is 365. How many hours in 1 day? It is 24 hours per day. How many? Oh, 24.นะครับแล้วพี่พลพิมพ์ VOI คืออะไร VOI voice over internet. I don't know, voice of information or what. Anyway, yes. Voice over internet, or I don't know. Yes, you have to convert 24 to how many minutes per 1 hour is 60 minutes. And how many seconds are there in 1 minute? It's 60 seconds, right? You have to convert everything into this, and then you get the half-life in second. Okay, and after that, you you leave it here, and N0 is right here, right? And after the calculation, right, you get this one 412 and 116.62 nuclei per second, and it's equal to this amount. If you convert it to 10 to 5, right? It's 5.1 10 to 5 decays per second. And if you want to convert to Curie, you have to divide by 3.7 10 to 10 decays per second. You get around 11.1 microcurie, okay, which is very, very small, very tiny value. The next thing is we're going to compute the remaining, right? Remaining radium nuclei. So N is equal to N0, and that's the 3 times 10 to 6, and 1 by 2 to the 3, right? You have to divide this number by 8, right? You have to divide that number by 8, and you get the remaining by 8. You get 3.75. 3.75, but the order is no longer 8. It's 10 to 15. Oh, this one is 16. So sorry, this is 16 in times 10 to 15, not 16 anymore. Nuclei, that's the remaining nuclei for the radium. And the last one is the radium. I don't know, the active decay rate at this time, right? Once you have these in, you just substitute this number, the half-life, in second to this one, right? So the next one is R equal, the number is ln 2 divided by this amount, okay, T 1 by 2, and you multiply it with 3.75 times 10 to 15. So times 10 to 15, you will get the resulting amount of nuclei. Oh, so that's the decay rate, right? Decay rate, microcurie. Okay, it's constant times 2. Okay, decay rate is you get the decay rates in the typical system as 5.5. Okay, 5.5, 5.15, 14577, 10 to 4 decays per second. And if you don't want it, okay, it's on the order of 50,000 decays per second. If you don't want, you want to convert it to Curie, it's also possible. You just divide this amount by 3.7 10 to 10, and that will correspond to 1.39 microcurie. Okay, and that's the result in Curie unit. All right, here you get everything about the decay rate. We have reached this topic, decay rate, okay, in this chapter, and we will see later next week, okay, on Wednesday, right? So the section for M605 would finish right here, and the homework would be homework here, the homework number 8, right? Homework number 8, it's something about decay rate, energy binding, or nucleus size. Okay, three possible problems. I'm going to create the 8 homework to you. Okay, นะครับก็605ก็คงจะจบไว้เพียงเท่านี้นะครับแล้วก็สร้างกันบ้านนะครับครั้งที่8นะครับกันบ้านครั้งที่8นะวิพล BOI มาคืออะไรงงครับสั่งกันบ้านครั้งที่8แล้วช่องนี้ช่อง Zoom to YouTube ไม่มีคนดูนะครับก็ปีรทัศน์นะพันธรพีรภพนี่ห้องไหนเนี่ยห้อง4ป่ะเนาะพีรภพน่าจะห้อง4นะธนทรเดี๋ยวพอดูก่อนนะ604จบที่อัญญะพิเชษพงษ์นะโอเคแน่นอนส่วนอันนี้พิเชษพงษ์อันที่2เอาปัณธรนี่คือห้อง5แล้วนะครับปัณธรห้อง5ก็ได้เก็บตั้งแต่ปัณธรนะครับปัณธรวลินทรหรอใครไม่รู้ว่าพิมพ์อะไรเล่นๆครับthis is the right yes the homework for the 19 lecture, but the 8 homework is this one, right? 8 homework assignment for today lecture, right? 8 homework today lecture is this one. Choose any topic of this one. This one, nuclear force, and the next one is defect mass. Defect mass and binding energy to no, it's 8 homework and 9 tools should be separate. Should separate from each other. Yes, so we have to key something. Yes, nucleus size, this one, right? It's one. I do it is 14. Okay, 14. Time is 09 00 and yes, that's the 8 homework and the 9 homework too, right? Các bạn hãy cao lắm. Night homework 072 and choose only one. The following two. Defect mass and binding energy and decay rate. Let's say on only 1 point. 1 point, it's 19 09 00 AM. Yes, sign. Yes, that's 2. And we have here 20 lecture right now. 20 lecture. Right, 20 lecture. นะครับ605 จบแล้วนะครับmaterial it's 20. Yes, 20 lecture. Yes, 20. Yes, these 3. Oh no, not one. Only 2 places, right? Yeah, 2 places. To open the widget. Same here. It's not this. Yes. It's 2, these 2. Anything else? Nothing else. Okay, finish.